At this point, you may be a little exhausted. This is a lot of definitions. For what reason? Well, look, learning how to differentiate is an important part of building a calculus, and that's our long-term goal, but there are also some short-term payoffs. Let's do some difficult examples and see what this differentiation really means. Let's consider a general one-form alpha that looks like f1 dx plus f2 dy plus f3 dz. Each of these fi is a scalar field on R3. What is the derivative of this general one-form field? By this inductive definition, it is df1 wedge dx plus df2 wedge dy plus df3 wedge dz. Now, each of these fi's has derivative equal to the gradient one form. It's partial fi partial x dx plus partial fi partial y dy plus partial fi partial z dz. That much we know. What happens when we wedge it up? Well, one of these terms is always going to die because dx wedge dx is 0, and dy wedge dy is 0, and dz wedge dz is 0. So let's do a bunch of algebra and assemble this together to compute d alpha. It is, for the first term, partial f1 partial y dy plus partial f1 partial z dz wedged with dx. The second term is given by what? Well, now a different term dies, and we get partial f2 partial x dx plus partial f2 partial z dz wedged with dy. That third term is partial f3 partial x dx plus partial f3 partial y dy wedged with dz. Now, this looks complicated. It is complicated, but based on what we know about the wedge product, we can do a little bit of rearrangement and simplification. Remember the anti-commutativity. When we switch the order, we get a minus sign. Now, you may want to take a little bit of scratch paper and go off and verify that what we get after rearrangement is partial f3 partial y minus partial f2 partial z times dy wedge dz. That's the first term. The second term is partial f1 partial z minus partial f3 partial x dz wedge dx. The third term is partial f2 partial x minus partial f1 partial y dx wedge dy. That is the two-form field. That is the derivative of this general one-form field. Now, again, you may have to go off and verify that with a little bit of work, but once you're done with that algebra, step back. Look at what you have found. This should be familiar. This looks like it's related to curl. More specifically, if we interpret alpha as the work one form associated to a vector field f that has components f1, f2, f3, then the derivative of this work one form is the flux two form of a certain vector field. What vector field? It is the curl of what we started with. Differentiation on one forms acts just like the curl operator. But instead of going from vector fields to vector fields, it goes from work one-form fields to flux two-form fields. That's kind of cool. Is that a coincidence? Well, let's see. Let's keep going, doing another example. Let's take a general two-form field in 3D. Let's say beta is f1 dy wedge dz plus f2 dz wedge dx plus f3 dx wedge dy. What is the derivative of beta? Well, we're getting good at this inductive definition. This is really df1 wedge dy wedge dz plus df2 wedge dz wedge dx plus df3 dx wedge dy, where again, each dfi is the gradient one form that we have already computed. Now, think about what happens when you wedge that gradient one form up with these basis two forms. Now, 2 out of 3 of these terms get zeroed out because of the fact that dxi wedge dxi is 0. So let's assemble this together. What are we going to get? The first term in d beta is partial f1 partial x dx wedge dy wedge dz. The second term is going to be partial f2 partial y dy wedge dz wedge dx. The other two terms vanish. In the last case, we have partial f3 partial z dz wedge dx wedge dy. Now again, we have a complicated looking three-form expression, but notice the cyclic ordering of the one-form terms implicit in the way that we've written things out, with a little bit of rearrangement using what we know about the wedge product. What we get is quantity partial f1 partial x plus partial f2 partial y plus partial f3 partial z dx wedge dy wedge dz. Look at that. Again, we see something familiar. If we interpret beta as the flux-2 form of a general vector field F with components f1, f2, f3, then the derivative of this flux-2 form of F is really the volume-3 form times the divergence of F. This means that when you're talking about two forms, differentiation is like the divergence operator. Now, is this a coincidence? What is this? This is a way to make sense of all the different types of derivatives that we have seen, gradients, curls, divergences, with one differentiation operator on form fields.